Yes, so this is called ArcticDB, Data Persistence with Consistency and Performance in a Truly Serverless System. My name is William Dealtry. I'm the architect of a project called ArcticDB. I've been a software developer for more than 20 years, and for quite a lot of that time, a member of the C++ standardization committee. I didn't start in finance, but I moved into the world of finance doing exchange data publication at the New York Stock Exchange and the Euronext exchanges, sort of pushing the data out of those exchanges. And since then, I've worked with really, really large data sets all across the finance industry, things like risk modeling and data engineering on the buy side and the sell side, which for those of you who don't know, kind of finance jargon, basically means hedge funds and investment banks. I think that ArcticDB is quite sort of unique in terms of the way that we work with the data storage architecture. And sort of to highlight that, I just want to give you a very brief tour of sort of how things have happened with data storage over the last kind of 20 or 30 years. So the original data storage architectures were called shared everything, and that meant you basically had a node, it had a disk, it had some memory, it had some compute. Clients connected to it via the network, and it served their queries. And a lot of the really big established relational databases like Postgres and MySQL and things like that, they were these kinds of systems. Slightly more recently, things have moved on to what's called a shared nothing architecture, and that's where you have a bunch of nodes, and they all have their own disk, their own RAM, their own compute, and they can't see any of the others' storage at all. They just talk to each other over the internet, and at the same time, they service clients over the network at the same time. So there's a lot of like very, very performant systems doing this, sort of replicating data between them. For time series, you have things like kind of Quasar. And there's ScyllaDB and things like that. They're all very much shared nothing architectures. Even more recently, we've started to move and see more of the what people call a shared storage architecture, and that's where the compute and the RAM is kind of local to where it's happening, and then that talks to the network, and behind that network you have a whole array of disks. This can be anything from hugely performant flash storage, cloud storage like S3 and Azure, or even just some MinIO cluster that you built out of things that you found in the skip. But what the clients do with their compute and their RAM is they just treat this thing as if it's one giant kind of logically addressable disk that they're working with. There are obviously some advantages to this, mainly other databases have to spend a lot of time thinking about availability, thinking about hardware failure, disk failure, node failure, passing replicas between each other, notifying each other something's changed. You can just defer all that onto the storage. You can rely on the underlying architecture to pass all the data around and make sure that you've got multiple copies. So if a disk catches fire, you don't lose all your data. Just vast capacity in them. And also, because of the economies of scale you get with these sorts of things, you can really kind of drive down the cost, and you can choose a cost model that you want. So if you want lots and lots of storage and you hardly access it, you can get super, super cheap, but with high egress costs, or you can sort of pay more for massive amounts of bandwidth. There are some drawbacks, one of which is the consistency models, whilst they've been getting better of these things, are still mostly eventual consistency. And if you're trying to address as many different kind of storages as you possibly can, then you end up with the intersection of all of the consistency models, the thing you can rely on from every single storage, and that is actually not very much. The other thing that you get with all of these different stores is that the performance can be quite variable. You can pretty much rely on read being good, write being good, delete being good. As soon as you start kind of listing things that require kind of indexing, then your mileage is going to seriously vary. So based on that, looking at data frame storage, there are kind of three things that are going on at the moment. You've got what's called OLAP servers, which stands for online analytical processing, usually the kind of shared everything or shared nothing model. Very, very performance and very high performance entrance in this kind of this category. They can be a little difficult to set up, and you've got a server running, so you need to monitor its health, you need to have something to restart it, or you need to pay someone to do that for you, so they can be a little fiddly to run. At the other end of the spectrum, we've got other kind of open columnar file formats. So that's all the things like Parquet and awk and things like that. Super low barrier to entry. Just write Parquet, read Parquet. Very, very easy to kind of get started with. If you have a couple of hundred of them, you don't really have a big problem. If you have, for example, about 20,000 libraries, some of which have millions of symbols, some of which have tens of thousands of versions, then you start to have a very, very large problem with some of these. And also, the model for kind of adding data or updating data is you read the whole thing out, you do some operations on it, you write it back in, and you hope that no one else has done the same thing at the same time, so that you're overwriting their changes or, they're overwriting your changes. This has led to the growth of what are called hybrid stores. And the idea with that is that you store the really big stuff in one of these open file formats often, or an extended version of one of them. And then you use some kind of ACID compliant server just to store the top level, which is usually called a catalog. So you get some of the benefits of having an open file format. You just write lots and lots of stuff directly to your storage, but then you get transactionality on top of that, which is kind of cool. The problem with that is you are still fundamentally setting up and running a server. So you've lost a little bit of that ease of use. You've created that point of failure, kind of brought it back in when it had gone away. And from a design point of view, once you have the catalog, there's a temptation to kind of put more and more stuff in it until you really just have a kind of, an OLAP server anyway, but with some stuff stored in S3. So what we wanted to do is to see how far we can push the consistency without a catalog. And to know that, you kind of have to know, well, what does the catalog do? And I think for that, you probably need to have a little bit of background in, like, what is columnar storage? What are we kind of talking about here? And the answer is that basically, all of these things are fundamentally quite the same. Ours, Parquets, awks, you name it. It's some kind of descriptor that's easy to access from lots of different languages and platforms. Could be protobuf. A little bit of logical metadata about the actual user data you're storing, some physical metadata about offsets and where things are, how many bytes do you need to skip if you're not interested in that sort of thing, the data itself, and then usually some other bits and pieces around kind of checksums and whatever. I mean, interestingly, this is very, very similar to what database files look like on disk. There's only really a couple of differences. One of which is they probably don't store everything in one tiny block. They'll amalgamate it into huge files, keep track of offsets within all of those. And then, maybe they'll have some storage that's quite fragmented where the new stuff goes, and then you'll have, gradually coalesce stuff into larger blocks and move it into the older storage. So the point of the catalog in the hybrid data store is basically just to solve this kind of data race thing. The problem that you have is you want to modify a block, someone else wants to modify a block of the same logical entity. And the danger is that you then get this Franken-data situation where you see part of that change, part of this change, and the whole thing is not a logically consistent entity at all. This is bad in lots of businesses. If you're trading billions of dollars based on that data, then it's particularly bad, and you really, really need to do that. So they're basically allowing you to do that block modification. So simply, you just need to basically stop modifying the blocks. Unfortunately, it's really, really hard to stop the users modifying any of their data. They don't really want to do that. So what you can do is you can try and create a store where the logical data changes, but the physical blocks basically stay the same. And that's called an immutable store. I think one of the most innovative original immutable stores was called Datomic, and it was done by Richard Hickey, who wrote Clojure. There's a really nice document store called Rethink, which is similar to Mongo. But the good thing is, if you never modify a block, then you can't corrupt your data, because when you modify stuff, that's when you can corrupt it. And also, you've got all that stuff from before, so you can travel back and you can see things as they were, either because you've reached a really good point in your research and you want to sort of freeze things at that point, or because you maybe made like a trading decision and you want to know what was the state of knowledge at that time. So what did we actually want to build with ArcticDB? Fundamentally, we just wanted a really, really simple, clean interface for storing persisting data, for doing data science, for doing quant research in Python. We wanted to decouple from any particular storage so that even within a single organization, you can use cloud storage, you can use, really, really expensive, super high bandwidth, super low latency flash storage, and you can also use cheaper storages for sort of research projects. We want to make efficient use of that storage space. And with all of that, we wanted to make something that performance-wise, competed with the really, really fast OLAP storages out there, but still just a Python module and somewhere to put the data, no servers, nothing to maintain, nothing to worry about failing and restarting. And so fundamentally, this is it. You can create an Arctic object. You can create a little library. This one's called PyData Global. And I can make a little data frame, a little simple toy one, and write it to the storage. And it just looks like that. Give it a symbol in a data frame, read. Obviously, if you want to read this, lib.read, and that's my data. It's a time series, with some numbers. It doesn't have to be a time series. There are two kind of challenges with immutable data and storage. One of which is, if you think you're doing immutable data, you need to be really, really sure that you don't overwrite those blocks, because then you're going to have like the world's worst corruption problem. And the second one is, if you're keeping every version of everything forever, then you really do need to be very careful about how you use the storage, or you're just going to end up, filling the disk and costing people lots and lots of money. The way that we solve the first problem is something called structured keys. And it's a kind of similar approach if you've ever seen, worked with something like a UUID. If you just want a universally unique identifier, what you do is you take lots and lots of different fields, all of which refer to something about when or where something was created, what it contains, and you end up with this unique identifier. One of the things about ArcticDB is it's really, really open to Python. Not only can you read and write your data to Python and you kind of divide it into chunks, you can go and you can dig around and you can see how we've stored it. So if I read the index of the thing that I just wrote with the 500,000 rows, we can see all these keys stored here, with a little bit of information about how it was all sliced up on the right-hand side. And that itself is also just a data frame. And as you would expect, if we look at the key type, this, the type of this data, because the keys are kind of semantically separated by what they mean, is table data. That means user data. That's something that someone actually put into the data store. So if I want to kind of add something on the end of this, but I don't want to copy the whole thing again, I need some kind of persistent structure that will let me do that. One of the ones that we use most is persistent B trees. And so if you imagine the thing I just wrote is all of these blue boxes, and the thing I want to add is the red boxes, I can basically kind of append some stuff. And then from the index here, you can see that all of the stuff up to the 500,000 lines is version ID 0, as in the stuff I first wrote. And then all of the stuff I've just added on, another 500,000 lines, is version 1. And you can see how this information helps us all kind of lay it out. Like I said, the first version is still there. We've got as of version 0, it's got 500,000 lines. Now we've got 1,000,000 lines. Sometimes, for reasons I don't understand, people like to read stuff out and just write it back exactly the same as it was before. And one of the really nice things about doing this is, if you do that, what happens is we do have 3 versions, but because we've detected that it's exactly the same data as it was before, no new actual data has been entered into the store. The same would be true if you kind of appended some data, but you did that by reading everything out, appending a bit, in Pandas or whatever, and writing it back. We would detect that most of this data is actually the same and just add on the delta of the stuff that you actually want. So we've got the data at the bottom, the index is above it. We then need to kind of track the versions as they evolve over time. And the way we do that is by having extra keys, and these are the version keys. And so you can look inside one of those, just as a data frame as usual. And what you can see is that it has 2 things in it. It has, if I print out the types of these keys, it has the index of the most recent thing, and it also has a pointer to the version key of the previous version. So in this case, we're creating kind of like a linked list inside the storage, where each of those previous keys points to the one before. And then when you get to the point where there's no new key, no further keys, you're at the beginning of the list. It also means that even these don't ever have to be modified at all, because you just read the most recent thing, then you make your new thing that points to that. and so on and so on. You're not kind of going in and modifying some version structure and sort of hoping that no one else is doing that at the same time. It has a fancy name. It's called event streaming. It just means that everything that happens, every update, every deletion, everything, it's all just, you know, an event that happens one after another, and we can always retrace everything that happened. And by default, we keep a record of all the versions that ever existed, even if the data's gone because it got deleted, just because the metadata overhead of that is really, really tiny. There is a bit of a snag, which is if you have these really long, unique keys, where do you actually start? What do you read first? Because the reader's not necessarily going to know the content hash and the timestamp and all of that stuff that the writer wrote. And sort of compounding this problem is that, you know, listing operations is quite variable across the different object stores. Sometimes you can read 1,000 things at a time or less, and then you have to get a continuation token. You have to make another request, you know, and then if there's some performance variability there as well, it can all get really slow. So doing that thousands of times, doing all these round trips to the storage just to read something is going to get a little bit sad. So what we do to solve that is we create a tiny little mutable entry just as a kind of reference point, as a speed up, to basically let us, you know, have an entry point to that. So you can see that for this library, I've got my entry point, and we can look inside that. It has 2 keys. The second of them actually points to the head of that version list we were looking at before. And then we cheated a tiny bit because the first one is actually the index key of the most recent thing. So for that super common case where you just actually want the most recent version of the data, you don't have to do any IOs to go and traverse that version list at all. If we know it's the latest one, you just grab this and you know, and you can go straight, read your index, you know, start doing some data processing. So you might be thinking, this is all very well, but you're spraying a lot of objects around in my object store, and is this not going to, you know, become kind of problematic over time? And indeed, you know, if I write another 10 versions, now I've got 12 of these things. But what we have is we have a whole bunch of operations that, for all of this kind of background metadata, they'll just go and clear everything up. They'll scoop it up into larger physical blocks, but, you know, the same logical content. And so if I do this, you can see, interestingly, that it's not compacted the very head of the queue, because that would give us consistency problems in this kind of inconsistent, you know, storage only environment. But the second one, all of those keys have been kind of swept up into one thing. So what's it for? Like, what do we kind of use these techniques for? ArcticDB is basically, it's a Python first data frame database. Because of the origins in the world of finance, where, you know, we have to deal with things like tick data from exchanges, built with intrinsic support for kind of changing schema, missing data, all that kind of stuff right from the outset. It supports multi-dimensional data, and you've also got all that kind of time travel and versioning of snapshots. I'd almost say it's a schemaless database, but that's not completely true. I mean, each data frame has a schema, and if you want to, you can tell us all of the schemas for all of the symbols whenever they get modified rather than, you know, overwritten, so updated or appended or whatever. It has to be the same. If I add a column, if I drop a column, that's a mistake. On the other hand, if you don't care, then and you want your schemas to evolve over time, you can, for example, you know, create this data frame with 3 columns. You can then create another one with 4 columns and, you know, extra floating point one. You can append it to the first one. And then we don't go modify anything about the first data frame, but what we do at read time is we just figure out where the columns are missing, and we backfill them with whatever the kind of type appropriate way to do that is. So, you know, reading and writing are nice. It's nice to have that, but I think the thing that we wanted to do before that is introduce some data transformations. And we don't kind of want to do the whole world of data transformations, because you can get the data out and, you know, you can use pandas, you can use PyArray, you can use polars, whatever you like, you know, to do further work on it. But there's a huge advantage to being able to transform the data as it's being read from storage. So as each chunk comes out of storage, you know, particularly in a case where it might be super large, it might not fit in memory, and also just for kind of efficiency, as the blocks are coming out, we're already transforming them. We're already getting them into this kind of like really workable state. So we've got this highly parallel vectorized execution pipeline. We actually recently refactored it. It uses something called an ECS architecture, which is borrowed from actually the world of games programming. Stands for entities, components, and systems. So an entity is kind of like a logical thing that you want to refer to that you're working on. It has this changing cast of kind of components underneath, which in our world are the kind of chunks of data and the slice information that goes with them, and all the other stuff like groups if we're doing some sort of partition. And then systems are these stateless kind of stages that just consume the entities and their components, and they basically kind of write them to write them to a new entity and pass it on to the next stage. So we're going to go a little bit bigger with the data now. I'm going to create a data frame with 10 million rows. There's going to be one row of random numbers between 0 and 1, just to crush any chance of good compression. And then a really high cardinality string column with 100,000 strings repeated not very many times, and then a low cardinality string column with 10 strings repeated loads and loads of times. And it'll take a little while to generate all those random strings. There we go. And so at the end of it, it just looks like this. We've got a numeric column, we've got our 100,000 strings column, and we've got our 10 string column. So in order to use this processing, we have this thing called the query builder. And what the query builder is basically, it's like a lazy data frame. So you can do a lot of the operations that would be familiar from Pandas on it. But rather than reading everything in and then starting to do operations, it will apply those operations in the correct sequence and as efficiently as we can with this kind of C++ vectorized engine, as they come in. So for example, if I want to choose all of the things which are less than 0.5 out of my uniform distribution of numbers, I can do that in 66 milliseconds over the 10 million rows. And what it looks like, as you would imagine, is around about half of those, so around about 5 million rows, which is kind of what you would expect given the distribution. You can also create columns on the fly, just as you can with Pandas Apply, which database people call projections, but I've learned since that nobody else does. So we're just going to times that numeric column by 2. Again, 81 milliseconds. And then here we go, we create this new column called new column. And that's it. I would say the thing with this is it's, the expression syntax will handle expressions of arbitrary complexity. The really useful thing about being able to do these applications is not so much on their own, although that's kind of cool. It's really being able to combine them with other things like aggregations and filters. So you can use an expression to combine the results of different columns, and then you can aggregate or you can filter based on that. And it really allows you to kind of express a lot of quite complicated data transformations. A classic one is hash joins, group bys, whatever you like to call them. So in 94 milliseconds, I can just join based on the highly repeated column and get the averages of all of those. As you'd expect, the mean tends towards 0.5 because it's that sort of uniform distribution. You can do the same thing in not very much more time over the 100,000, coming up to kind of half a second to do that. And interestingly, you see a little bit more spread because the law of large numbers is not applying quite so much. You've got fewer things in each, so they're kind of spreading a little bit either side of the 0.5. But like I said, the really, really cool thing about it is the fact that you can just chain all these things together. So you can create a new column, you can group by it, you can do multiple aggregations at the same time. Almost one of the interesting things is, one of the slow things sometimes about Python is you've got to hold a GIL to allocate strings. There's sometimes some copying inside Python that happens. The more you can do before you have to actually present the results to Python, the more sort of use you can really get out of these. So there you go. That's the mean of the numeric one tending towards 0.5 again, and then the max of the other one obviously tending towards 2 as we've multiplied it. What are we doing at the moment? So Arrow support is working in a branch not quite ready for PI yet. Resampling along the lines of Pandas resample, and also sorting and merging. So you can really kind of just blast data in parallel, really, really useful if you have kind of multi-process or you've got a big Spark cluster or something like that. It can be all out of order and overlapping, but then if you want to have it as one symbol, we'll go in and sort those things individually and then merge them all together. So you get one kind of perfectly sorted time series, but you can really kind of spread the work out. In future, we want to do kind of native Spark support, joins, which are kind of actually technically similar to aggregations. A thing I think is going to be really, really useful is called spill to storage. And what that means is that if you are doing a computation and even the kind of intermediate stages won't fit in memory, what we can do is we can take the ones which are kind of partially done or finished with, we can write those back to the storage as a kind of ephemeral chunk, and then free up some RAM to continue doing the thing we were working on before. And then at the end, we can either take that series and we can write it back down to the storage if it's too big to read, or we can just, if the result set fits in memory, then we can return it to you. We're probably going to introduce a way to kind of read stuff in chunks as well. So if you've got a result that doesn't fit in memory, you can have a chunk and then ask for the next chunk and exhaust an iterator. We're also going to work on being able to compact, like I said, with databases across symbols. So if you have a really, really massive history of versions, actually combine them into really massive chunks to to put those maybe in your Glacier storage or tape or whatever you like. So that is it. If you would like to know more, then you can find us at our website, which is arcticdb.io. It actually has notebooks there. You can go and actually play around with it just right on the website. Interested in the code, then hit us up on GitHub and maybe give us a star. And if you want to try it in your local environment, then pip install, conda install, whatever you like. Thank you very much.
Thank you, William. So we have a bit of time left for some questions there. I think there was one put in the chat, but it sounds like you may have answered it if you want to take a quick look. Are there any questions from the audience this time? You can either put them in chat or in the Q&A section.
Can you share what the system specs are if you're running it locally? I am not entirely sure. I'm sorry. I think it's probably got about, I think there's probably about 10 cores on it and reasonable amounts of RAM. But, actually, I only went on this one because normally we demo on an OpenStack and K8 based kind of on-demand notebook, and the performance is not that much worse, but it's like a time slice dual core thing with 8 gig of RAM. And it's a bit sad because obviously one of the advantages of C++, we get lots of parallelism, so then we're doing it with 2 cores where there's almost no parallelism at all, and the 8 gig makes me super nervous for this sort of thing. Just I couldn't generate it is the main thing. I could probably read it, but I couldn't do the generation. So I think it's probably got about 64 gigs of RAM, but I'm genuinely not sure. I just borrowed this machine for the talk. I can let you know.